Okay, folks, I will start again. So I was going to put up this slide again to confirm that Ilya got it right. Um, and I love the style of being able to do dimensional analysis to get quantities like this. And actually, I put up the slide for a couple of other reasons. One is that of course, what Ilya didn't get right was the 5 over 96. Okay, and it is characteristic, as you probably have seen before, and you'll see a lot more in the next short while, that when doing calculations in general relativity, you often get remarkably interesting integers. And so we'll see some examples of that later. 5 is not a number that shows up a whole lot in physics, but it shows up a lot in general relativity for interesting reasons. He also mentioned only, but didn't include in his derivation, the 1 over the symmetric mass ratio. So as the system gets more and more asymmetric in masses, the chirp time gets longer and longer, exacerbating the problem that Ilya will solve for us later on tomorrow. The other reason why I wanted to mention it is because notice that this chirp time is labeled tau 0, and Ilya pointed out that he's calculating a time that's on the order of the binary separation divided by dA by dt. And when he did that, he argued, these things are changing and you really got to do a proper integral. And when you do that, of course, you get corrections to this. And those corrections, and including higher order terms in the relativistic corrections, will produce a whole perturbation expansion, or an expansion of times t0. Actually, the next order one is labeled t3, which is the 3/2 post-Newtonian correction to it, which is pretty small in most cases. And then there are higher order corrections, and you're going to see them as well later on in this lecture. Higher order corrections, but this is the dominant one when you're very far from merger. Okay, so those are the reasons why I wanted to bring up this slide again. Are there any questions? Okay, so I'm going to then try to skip over to where I was. Where I ended last time, and I ended with outlining the 15 parameters that are that describes a circular binary far enough from merger. And again, the important ones are the intrinsic ones, the masses and the spins, and I'll talk more about spins shortly. And the extrinsic ones govern basically just the loudness, the amplitude of the signal as received from the detector. But there was this extra caveat, and this extra caveat about spins and orbital angular momentum is important, and I was going to talk about it later, like maybe in tomorrow's lecture, but Ilya brought it up, so I thought this is a good opportunity to talk a little bit more about this extra complexity that shows up. So we'll talk about spin-orbit type interactions well, let's see, maybe we'll talk about it right now. So let's talk about it just a little bit. Okay, so let's see, I have a pointer. Here it is. Okay, so if the black holes have spin, and in general, everything is spinning in the universe. Astrophysical black holes will always be spinning at some level. Then in this little tiny diagram that you've probably seen before, here's two black holes with spin spinning around and orbiting each other. And this is already, especially in LIGO-type sources, an extreme situation, because what you've really got, black holes aren't matter or anything spinning around. They're curved space, and as they spin around, from their spin angular momentum, they drag the space around them. That's frame dragging. It's been measured beautifully by Gravity Probe B, amongst other things. Just from, Gravity Probe B was just orbiting the Earth and measuring the frame dragging of the space-time around the Earth due to the spin of the Earth. So it's a small but measurable effect in the case of the Earth, but in the case of black holes, can be a very, very big effect. So what you really have here is a tornado of space-time. That's why it's drawn in this cute little, I should have made this bigger, this cute little diagram is a tornado of space-time spinning around. And you know what? Next to it is another tornado of space-time. And you know what? They're both orbiting each other in a third tornado of space-time. Okay? This is an immensely complicated system. Okay? And because space-time extends out to infinity, this tornado of space-time is affecting that one. And they're affecting the orbit. And so naturally, you get couplings between the spin of one black hole and the other and the orbital angular momentum. Spin-orbit couplings produced dynamical effects, as well as spin-spin couplings produce dynamical effects, as we will see. Most of you have studied the hydrogen atom. You've probably learned about spin-orbit and spin-spin hyperfine couplings in the hydrogen atom. And that's due to this physical thing, this electromagnetic field that's produced through the spinning of charged particles, magnetic moments and the like. What's happening here is not through any intermediary other than space-time itself. And it's and it's an important effect. It shows up at higher order in the post-Newtonian expansion, as you'll see. And so it's of great interest to people. And what happens due to this spin-orbit coupling is that the orbital angular momentum normal to the plane of the binary, it's not easy to see, but imagine L is normal to this orbital plane. Here's the spin of M1 and the spin of M2, and they add up to a total spin. So let's take the orbital angular momentum and the spin angular momentum, and they add together to get the total angular momentum. And the total angular momentum, as I mentioned, is not exactly conserved, but it's close to being exactly conserved because the gravitational waves that are emitted don't carry away that much angular momentum. And so you can imagine that the total angular momentum is fixed in space, and then as the spin-orbit interaction causes these two vectors to precess around the total angular momentum, and that means that the orbit itself is wobbling. Okay, and Tom showed a lovely little simulation of that. The time scale for that wobble is much slower than the orbital period, but it is maybe on the order, it's not much slower, on the order of maybe an order of magnitude slower. Okay? So over maybe on something like 10 cycles, you would see this orbit precess. See it, or 10 or 100 cycles, you would see this orbit precess. And the precession of the orbit will have an effect on our detection, on the waveform that we observe at the detector, because because there's a pattern at which the gravitational waves are beamed, and that's changing because the orbital orientation is changing. And then, as it reaches the detector response sees basically changing amounts of the two polarizations plus and cross, and the different responses of the response of the detector to plus and to cross polarization is different, and so we will end up with an amplitude modulation of the signal, which is an observational effect. It's not something that is happening at the source. It's what's happening at the detector. Okay, so if you were to ask. And this happens only if the spin angular momentum is not aligned with the orbital angular momentum. And so here are just some definitions. This is the spin angular momentum of the two black holes. Here it is normalized to the dimensionless Kerr spin parameter, which is between 0 and 1. Here is the component of that is aligned with the orbital angular momentum for the two black holes, and here's their mass-weighted combination. This is what we call the effective chi parameter, the effective aligned spin parameter. It can be positive, it can be negative, it can run anywhere between +1 and -1. And here is the component of the spin perpendicular to the orbital angular momentum for the two guys, and here's the mass ratio Q, which is a number less than 1 in this formalism, and chi p is a measure of the degree to which the orbital plane precesses. Okay, Why is this even very important and interesting? Well, of course, it's important and interesting if you want to study this kind of relativistic dynamics, but it's also important astrophysically. And Ilya will probably tell you a lot more about it, but let me just give you the two-liner, okay? And that is that we want to know how binaries form, and we have basically two big models of how they form. One is that the two stars form together, maybe originally from the same swirling gas cloud that condensed via the gene's instability into one massive star and a second massive star, orbiting each other lazily for billions of years. And then they go supernova, and then they produce a binary, a compact binary, which eventually merges, maybe in 10 to the 14 years. You expect that the spins of the two black holes will be aligned with the orbital angular momentum because it was all formed from the same common swirling gas cloud. Okay, so you'd expect. Now, of course, you don't expect it to be perfect because supernovas will cause the spins to get kicked away from their original value. But actually, the estimates of that for real astrophysical systems is that misalignment of the spin parameters are small. Okay, but you expect more or less aligned spin and orbital angular momentum and very little precession. Okay. The alternative model is that the binaries were formed dynamically. That is to say, the stars form totally independent of each other with spins that are totally independent of each other. One's pointing in this direction, the other's pointing in this direction. They get dynamically captured through three-body or n-body interactions into a binary in which there's no correlation between spin 1, spin 2, and orbital angular momentum. Measuring the spins is one of the best ways of distinguishing between these two formation scenarios. So that's another reason why it makes it interesting. There's another reason why it's interesting. When these guys merge, if all the spins are aligned, then you could add up the orbital angular momentum and the spin angular momentum and get a number greater than 1 for the final merged black hole. That's no good. That's not a Kerr black hole because you got too much angular momentum. You got to get rid of that angular momentum, and the only way you can do that is by radiation of gravitational waves. And what that results in the dynamics is that it is what used to be called anyway, orbital hang-up. Okay, whereby the chirp, the in-spiral, lasts longer, sometimes much longer, than it would have if there were no spins, before they finally can get rid of enough orbital angular momentum, enough total angular momentum to merge into a single black hole. Okay, if the spins are anti-aligned, then the waveform will be shorter than in the absence of spins, longer, shorter. Okay. Another interesting thing that happens is that the spins are just so when they orbit each other, when they merge, you can end up with a situation where the spins all point in some other direction, okay, and that will produce a beaming of gravitational waves in that direction. And gravitational waves are hard to beam, but you can do this. Okay, I mean, it happens. When they merge with the spins aligned in just so, then the gravitational waves can be beamed in one direction, and then the final merged black hole recoils in the other direction. And that's called a natal kick, a birth kick of a black hole. And that black hole can go flying off, sometimes with escape velocity with respect to the galaxy that it's in, and that black hole can exit the galaxy. Okay, yeah. Uh-huh, so I'm not sure about the right answer to your question, but I can imagine that a very strong beam gravitational wave can accelerate particles, massive objects surfing on the wave, and accelerate in the direction of the gravitational wave. if those particles are very, very close and feeling a very, very strong gravitational wave. Possibly, yeah. So there have been many simulations to see what pro, if you were to assume that the original black holes were isotropically distributed, what's the probability of getting a very strong natal kick? And by very strong, I mean escape velocity from a galaxy. It's a very small probability. But there's a lot of these things in the universe, believe it or not. And even though Ilya is going to, and Ilya will tell us why, because he said there shouldn't be any. But he'll tell us why there's actually a fair number. Why we've observed already 6. And I think the probabilities are small, like much less than 1%, that you have a very strong kick. Okay. But I'm hand waving, and I'm just remembering something I read. Okay. Yeah. Hmm. Interesting question that I don't know the answer to. Is anyone? I mean, I would assume that imparting a lot of linear momentum to something, like the black hole, is a form of perturbation. Exciting quasi-normal modes I mean, it's enough to have excited quasi-normal modes associated with a merger. That's a pretty darn strong perturbation. Whether the natal kicks are strong enough to produce a noticeable further excitation is an interesting question. It's a matter of the numbers that I don't know. Interesting. Okay, so I just wanted to talk about that because there's a lot of interesting aspects to it. But at the most immediate level, we would like to measure spins well enough. Yeah. Yes. Um, so uh, it's because of the dynamics, the post-Newtonian dynamics, which we'll talk about in a minute, that of the spin-orbit interactions. But it also should be reasonable to get your brain around intuitively, because after all, in the absence of spin, there's one time scale, that chirp time scale that I showed you. In the presence of a line spin, that time scale is longer, so it's natural to imagine that when they're anti-aligned, less less total angular momentum to get rid of, easier to merge. I'll mention that before, 10 years ago, before numerical relativity had its successes and was able to work with spinning black holes, it used to be thought that this aligned spin orbital hang-up, where has to take a long time to merge, could have been associated with extremely complicated strong interaction spin-orbit dynamics that would cause the spins to flip before merging, making it easier for them to merge. That has not been seen in numerical simulations. So it was thought that the merger would be a very complicated event with these spin flips. But there's been no evidence of that. The merger is about as boring as it can be, just another cycle or two. Yeah, yeah, that's right. That's right. Okay. All right, well, let's go on. Oh, I just wanted to show you this because it will come up much later on Friday. Well, I'll talk about how he measures these spins, but you'll hear much more about it from John Veach next week. But as Ilya mentioned, the high mass X-ray binaries suggest that X-ray binaries in our galaxy suggest that spins can be very, very high, and we just haven't been able to see it. We really don't measure spin very well. We measure it very poorly. But I wanted to show you what the results look like. So these are complicated plots. This is the more massive black hole. This is the less massive one. This is aligned spin, and this is spin in the orbital plane, which is precessing spin. Okay? And this is a posterior probability distribution function for GW150914 and GW151226. and some combination of this vertical guy, this vertical spin axis, and this one, M1 and M2, is chi effective. And so here's chi effective on this projection, and here's chi precessing on this one. And what is hard to see is that there is a green curve here, which is the prior, assuming isotropic spin directions and and spin magnitudes flat between 0 and 1, which is crazy. You see that in the case of the precession spin, the prior, maybe you can see it, maybe you can't, the prior and the posterior are look the same. In other words, there's almost no information in the data. We really need SNRs of 50 or 100 to start measuring these things well. This blob of blue is the posterior distribution function. It's all over the place. Okay? A line spin should be up here. Precessing spin should be like this. This is what we might expect for common evolution of two stars. And we don't see it. Okay. But I'll talk more about it later. Okay, more parameters. Eccentricity. So as we talked about last time, gravitational radiation circularizes eccentric orbits long before it gets into the LIGO band, usually, unless it was captured into a very tight elliptical orbit. So if the binary is performed through dynamical capture in a tight eccentric orbit, then more parameters are needed to describe it. Okay, and there's the eccentricity itself, the angular location and phase, orbital phase, of the so-called periapsis. There's more parameters that would be needed to describe tidal distortion and disruption of neutron stars, hypermassive, whoa, two massives, that's a lot of mass, hypermassive neutron stars and their properties, and potentially beyond GR effects like deviations of the post-Newtonian expansion as the speed approaches the speed of light. Any disagreement between the observed final black hole mass and spin from predictions from the component masses and spins. There's a unique prediction. You tell me the component masses and spins, and then from numerical relativity, I know what the final mass and spin should be. And deviations from black hole ring downs, higher modes in the ring downs, from black hole perturbation theory. And this is there's a long list. Yeah. And damping times, the complex frequencies. Look, the bottom line is that GR is an extremely constrained theory, and historically it's insanely hard to come up with theories that aren't tiny perturbations on GR that are still agree with all observations so far. And in fact, LIGO has killed a whole class of scalar tensor theories, Horndecky theories, all kinds of theories are just gone after the first LIGO observation. Oh yeah, how much it is excited, the amplitude of them. Absolutely, yes, that's a test. It's a great test which we will one day be able to do. Excellent. Yeah. What else did I want to say in this slide? So there's a lot more parameters you can add. Oh, what I wanted to say in the previous slide is that if you start with intrinsic parameters, M1, M2, and 3 spins, and another 3 spins, that's 8 intrinsic parameters. That's a large parameter space. That's why we choose these two guys, chi effective and chi precession, to reduce the parameter space from 6 spin components to only 2. And we're allowed to do that because much study has shown that it's only these 2 that have the dominant effect on the phase evolution of the waveform. Whew, we don't need all 6. That's good. Of course, you could argue, I knew that already because there's isotropy of nature. So there's at least one that's not important. Okay. Does that make sense? Okay. Right. So back to the waveforms themselves. So in order to model these waveforms, well, you're going to do it to lowest order in the quadrupole approximation. Okay? You're going to do it in the assignment that I gave you. So it's not that hard in the just using the quadrupole approximation, and that gives you the early in spiral. And as you go to later and later in parts of the in spiral, the velocity increases, and you have to include more and more relativistic effects. When you get close to merger, forget it. This expansion, the post-Newtonian expansion, is not a controlled perturbation expansion. Okay? There's no guarantee that it will converge. It's not like a Taylor series with a convergence a radius that you can calculate from first principles. There's no guarantee that it'll converge. Okay? So the fact that it works at all is actually kind of a little bit of a minor miracle. Okay? Even though it's an expansion in powers of V over C, and you think that as long as V over C is small, it's a series that will converge, there's no guarantee at all of convergence. Okay, and you will calculate this by to the lowest order in post-Newtonian expansion, that is the quadrupole formula, but you can go to higher orders, and by taking into account that the orbital energy and the flux, you can numerically evolve a waveform. Yeah?
So, what are the assumptions in which the post-Newtonian can hold?
Right. First of all, it's only been worked out in the simplest case, the two-body problem. Okay? Actually, that's the limit of my knowledge. Okay? Yeah, that's pretty much the limit of my knowledge. You got a two-body system orbiting nicely. It includes spin, and it includes eccentricity. Experts in the audience, is there more that we can say? That agree with numerical relativity, and guess what? They agree with observation now. It's really a thrill. And there was no guarantee of this. Okay? No guarantee. Okay. But certainly by the time you get close to merger and the ring down, there's, don't expect it. So I'm not an expert, but I'm going to quickly show you some formulas. Okay? Oh, formulas galore. Okay. Sorry. You can compute the post-Newtonian orbital energy. Ilya did this on the blackboard. That's the first term, the Newtonian term. You know it well. Minus 1/2 you can write it as either g m1 m2 over r or over a or whatever, or you can write it as 1/2 mv squared. And this is the symmetric mass ratio, eta. Do I define it anywhere? Jesus. All right. Well, I should define it somewhere. These are higher order terms, which are powers in v squared, v to the fourth, and v to the sixth, and so on. Okay, so they're powers of v over c squared. Okay, and this is without spin, but there are much longer formulas including spin. Okay, that's the energy in the orbit. This is the energy loss, the flux. Okay. Here's where it's nice to point out these integers. I don't know, they blow my mind. I don't know if you experts can tell me why we get integers like, 44, 7, 11. I mean, really? This comes out of some math. And it's an integer. It's not like an approximate number. Okay? It blows my mind. They're exact numbers. Well, to lowest order, to that order of perturbation theory. With these two things, you can evolve a waveform, okay? And get in the time domain the strain in terms of the phase. And the phase evolution, the phase is a function of time, is just from, you can get it just from Kepler's laws, and it's just v cubed over m. This is just the velocity, and the evolution of the velocity is given by the energy loss divided by the energy. Okay? That's it. That's all you need. Okay, to evolve waveforms and to evolve and get waveforms h of t, which basically go like the cosine of 2 phi of t. Okay, that's the phase of the waveform. In all these terms, the velocity is simply related to the gravitational wave frequency, and the time scale is given by well, this expression. And then, so you can start with energy and flux and evolve a waveform, or you can let somebody else do the work for you. And Luc Blanchet and Thibaut Damour and a whole slew of people have done these calculations to higher and higher orders in perturbation theory, in post-Newtonian expansion, and go straight to a perturbation expansion on the phase, rather than getting the phase by evolving this energy and energy loss. You can go straight to the phase itself and evolve that, and the amplitude itself. Okay? Yeah. Yeah, none of this has spin in it yet. Oh, yes, and I'm not going to show it to you. Here's what I'll show you. Here's what I'll show you. I'll skip to it. Here's a schematic of what, the forces, if you could write it in terms of forces, what they look like for spin. Here, okay, so this fellow over here likes to use epsilon instead of v over c squared. Whatever. You see, there's a Newtonian piece. There's a first, second, and higher order post-Newtonian pieces to the effective force that accelerates a particle. This is quite general, actually. Here is the first, the lowest order in which the spin-orbit interaction happens. This one is the what's happening is that one star is tidally distorting the other. These are black holes, okay? And it's tidally distorting black holes and inducing a quadrupole moment on the black hole, on its companion, and vice versa. Okay? And that quadrupole moment interacts with the orbital angular momentum. Okay? So that's this term. This term, I should say. This is the radiation reaction term. This is a back action term. The radiation is emitted, and so you lose it. So the objects, the two black holes lose energy, and there's a radiation reaction to that. And it's a relativistic effect, so it involves time delays. Okay, so it's a complicated. Took years of work to get the radiation reaction term. I believe this is to 2.5 post-Newtonian order. More post-Newtonian things. Here's the spin orbit, and finally, and quadrupole. Finally, there's a spin-spin term. That's the third order in post-Newtonian theory, or v over c to the 6. And even not only quadrupoles, but this is what the heck is the T? The octupole orbit coupling. Whoa, these guys are so amazing that I don't know, you spend your life doing this, I guess. Yeah. So when we talk about tidal deformability of neutron stars, we're talking about tidal deformability over and above the space-time they occupy. Black holes, don't let anybody tell you that black holes don't have any tidal deformability. Of course they do. The space-time is being tidally deformed. They have to be, right? So it's often said that black holes are not tidally deformed. Of course they are. You can see it in the movies that I showed you, right? These blobs, these black blobs start out as spheres. When they come close to each other, they are not spheres. They're obviously being tidally deformed. Proof by movie. That movie is not an artist's conception. It's a supercomputer simulation. Okay. There's a term in here, I'm not even sure which one it is, which is the tail term. And at this point, I'm going to close my mouth and ask Tom to tell us what the bloody tail term is. It's the most difficult part. Well, it's hard to calculate, but also it depends on the entire past history of the evolution of the binary. And it's also famous for making it clear that this is not a controlled expansion because it's really big. Even though it's high order in this expansion, it's a really big term. In fact, it's bigger than a lot of the lower order terms. So that's not a controlled expansion. Yeah.
During my talk, I said about the branch, but in the green function, I never mentioned. But they have the the late time response of the black hole perturbation is given by that table there. But I'm not sure if it's
I think
something
that's right. I
you
think they're related.
or if they are related
I think
somehow.
they're related somehow.
I think they are reflections, but then their order is cut out as reflections too. You're just getting the lowest order of the wave scattering off the space that get energy related in that fraction. The interpretation is the same.
And these are fundamentally relativistic things. They have to do with time delays. So, just you got to look at a lot of history. Everything builds up in the space-time that you're living in. So it's really complicated. I'm way over my expertise here, so I'm going to continue. Um, yeah. No, no, it's doing this right. Uh, so these formulas are just energy and energy loss, and then you can write it in terms of the strain and the phase evolution, or equivalently, you can write it in terms of separation loss, A dot, or period loss, P dot. You can write it in many different ways. They're all saying the same thing. Of course, I only know what the lowest order in perturbation in post-Newtonian, but there's a p dot that's related to p in a formula as simple as this. I mean, as simple as this. Well, as simple as the first term, because that's all I know about. But there are higher order terms in that expansion as well. So people do it several different ways. Okay? You'll get the same answer whether you consider energy loss, angular momentum loss, radial separation loss, period loss, or go all the way to the waveforms themselves. All of those are equivalent formulations. Entropy? Oy vey. This is a two-body problem. Well, there are these tidal terms that do take into account the fact that this is a finite-sized object. Yes, yes. So it's an interesting question, which I know nothing about. All right, so I'm going to go beyond all this. And here, by the way, you can finally end up with a formula for the waveform in the frequency domain, which you can Fourier transform to get it in the time domain. And amplitude, there's that f to the minus 7/6 that Ilya pointed out. And here's the phase evolution, not in time, but in frequency. And once again, there is a post-Newtonian expansion in terms of these unbelievable numbers. And again, these are integers. Uh, I don't know. I don't know. Some of them are integers and mind-blowingly long integers, and some of them are numbers like the Euler number or the gamma. What is gamma? It's an Euler number of some kind. Okay, I don't know how Euler numbers show up here, but they do. Okay. These guys know. Okay. So this will give you an inspiral until it breaks down. And the merger, the PN expansion fails as V over C goes to 1 as we approach merger. And after merger, the final merged black hole rings down as described by black hole perturbation theory. We just heard a very nice talk about it. And in between, you need full general relativity. No analytical solution is known. So instead, we numerically solve the GR field equations, and it's very complex, and you'll hear a lot more about it from Harold. These simulations take months, even just for a few orbits. The actual the SX simulating extreme spacetimes collaboration have the longest waveforms. They're up to 33 cycles. Actually, I think they're up to over 100 cycles now. Nobody else comes close because they use these interesting spectral methods. Yeah,
Where does the effective body theory help us in research?
I'll get to that.
Okay.
Okay, so I'll get to that. All right, so analytic waveforms for the inspiral are increasingly less accurate. Here's a plot of f of t versus time, so frequency versus time, close to merger. And here are different ways of computing the post-Newtonian expansion. And oh my gosh, they don't even agree with each other. And they're all post-Newtonian expansion. There are different ways of doing it. Okay? And they don't even agree with each other, much less with, full GR. Um, and this is evolving up to ISCO. And, the pod A approximation, the EOB approximation, they don't even agree with each other. Okay? And you can see that what that means is that the phase evolution is such that you'll produce differences in the phasing that can be as large as a whole cycle. So you can go from a match filter with constructive interference to one with destructive interference, losing your signal-to-noise ratio. If you get this wrong, you'll lose SNR. We can't afford to get this wrong. We just spent $1 billion on these detectors. So what do we do? Well, numerical relativity to the rescue. So it's now possible to accurately calculate the latest final stages of in-spiral merger and subsequent ring down, even with spin. And even with eccentricity. In fact, it's hard to get rid of eccentricity in these numerical simulations. But you can only do it for the last handful of cycles. So what people do is take the in-spiral, which is this red thing, the post-Newtonian in-spiral, which is this red thing, and the numerical relativity, which is this blue thing, and find a place where they agree. And where they agree, you stitch them together. And you need to do that because you've only got a few cycles of in-spiral from the numerical relativity. In this case, it's about 10 or 15. But you need a waveform extending back to frequencies of 20 hertz where the LIGO band starts. You need the full waveform. So we need to stitch together the post-Newtonian part with the numerical relativity part. Okay? So how do you do that? Well, you can do it. Oh, and then there's the black hole ring down. And the ring down, once again, as we just heard a lovely talk about. First Okay? Uh, you can see that the time scales for f dot um, dramatically changed close to merger. The frequency ramps up very, very quickly. That's going to be our tau 3 and tau 4 and tau 5 until it goes out of control. And here's the ring down at one frequency, more or less. That's the dominant Y22 mode of the ring down. It's a quasi-normal. Here's an exponentially damped sinusoid. Here's an exponentially damped sinusoid. Its Fourier transform, and the frequency domain is a Lorentzian. And here I show the difference between a Lorentzian and a Gaussian to remind you that they are different waves. They are different line shapes in the frequency domain, and neither of them are airy peaks. Okay. And governed by quasi-normal modes, which are indexed by these spin-weighted spherical harmonics L, M, and N, which we heard a whole talk about how you can calculate them. And there's some formulas. So that's analytical or semi-analytical. Actually, these calculations here are numerical. The coefficients in front. You heard all about it. We can ask, can we just use the numerical relativity waveforms? First of all, they're short. They currently span only the last few or tens of cycles to merger. We need to extend backward into the detection band, the minimum frequency, by stitching to a post-Newtonian analytical waveform. But more importantly, they're very expensive to compute. And we need to cover a large parameter space, right? Masses and spins. Okay, that's again 8 parameters, 2 masses, 2 spin vectors. This is a large space. And by the way, it's not 8-dimensional. It's 7-dimensional. Why? Mass goes out. Why does mass go out? Total mass. Goes out because general relativity is a scale-independent theory. Bless you. There's no preferred scale. You pick a mass, and your solution to some general relativistic problem works for some other mass as well. You know how to scale it. Everything scales with g times m. So the total mass just pulls out. If you compute a numerical relativity waveform for m1, m2, so you've got a total mass and you've got a mass ratio, then you can easily go to a different total mass with the same mass ratio by scaling. In the case of these waveforms, the amplitude scales very simply with mass to the 5/6 power, and the phase evolution is the same in the time domain, for example. It's the same if you change the time axis or measure the time in units of mass. So you can take a numerical relativity solution for a 100 solar mass binary black hole system and use it for a 10 or 13 solar mass binary black hole system right off the bat. Yeah. Yeah. Can you what? Sure, but whatever mass you've got, you will still approach merger. And as you approach merger, this breaks down. Does that make sense? Okay. So everything goes like not the frequency, but the frequency times the mass. So you can easily scale to a different set of masses with different frequencies. The merger will all be different at a frequency of, the merger happens at a frequency of 1 over m. Also, we need to have a smooth, continuous coverage of the parameter space, especially for parameter estimation. Here's one thing you could try. Here's a signal. We found it in the data. And now we want to fit it to a bunch of different waveforms with different values of the parameters and see what fits best. So we pick one point in parameter space. We're going to walk around in parameter space with a Markov chain Monte Carlo. You pick one point in parameter space, some masses and spins, okay? And then you run across the street and you tell your numerical relativity colleagues, calculate me a waveform for these parameters. And they go, no problem, no problem. And 3 months later, they come back and they give you a waveform. and you calculate and you figure out, just what how well it matches the data. And then you find another point in parameter space. You go across the street. You say, make me a waveform for those parameters. 3 months later, they give you a waveform. And then you do that 500 million times. Okay? And then you can get, a convergence of your parameter estimation Bayesian inference analysis. Okay? It's not going to work. You need to compute waveforms not in months, not in minutes, not in seconds. You need to do it in milliseconds. Okay? We actually have a hard time doing that. Okay? But in order to do it, you need a phenomenological model that agrees with the post-Newtonian one, which is easy to calculate, and agrees with the numerical one, which is really hard to calculate, in milliseconds of computer time. That's what you need. There's a variety of ways of doing it, and we have several different waveform families that do it in various ways. Right now, the favored ones are these things called IMR phenom, or spin EOBNR, which are parameterized models that agree with these waveforms for a few points in parameter space, including a line spin and precessing spin, and allow you to interpolate between them. Another approach is to take a handful of numerical relativity waveforms, say 50 or 100, put it in a library, and then use fancy numerical techniques called reduced order modeling or reduced order quadrature to interpolate between them numerically. That's what we have to do. Oh, here's how we stitch things together, but we have to stitch between the post-Newtonian and the merger waveforms, and you do that for a handful. You've only got a handful, or tens, of numerical relativity waveforms, and then you hope you can interpolate between them. So here's a very nice one, EOBNR. This one doesn't include spin. There's a spin version, which is very, very slow to calculate, and it agrees beautifully well with the numerical relativity in the region in which it's been tuned to agree well with numerical relativity. And by agree well, I mean that you got to get every one of those cycles right for many, many cycles. Otherwise, you'll end up losing signal-to-noise ratio. Okay, so we have a bunch of these. Okay, different groups have developed in spiral merger ring down waveform families that can be quickly computed from input parameters. If you're including spin, 10 parameters for quasi-circular orbits with a line spin and up to 15 with generic spin. And many of these have been produced. You'll hear the names: IMR phenom B, IMR phenom P. The P is for precessing with non-aligned spins, SEOBNR V4 and V3, and so on. This is very, very slow. If you actually go into PyCBC and ask what waveforms are available, it lists quite a large number. Okay? Only a few of them are like the mature, evolved ones, including spin, and only one or two include eccentricity. Let's see. Effective spin, somewhere around here. I don't know where it is in the C, but you'll find one like an eccentric time domain. There's one or two of these. Okay, really not too many. Here are the ones that we use for example, GW 1708, 17. Actually, 1708, 14, our binary neutron star. This is, wait a minute. Oh, no, 17 is the binary neutron star. And it is it's SEOBNR with tidal effects beyond the tidal effects associated with black holes. Phenom D is sort of an evolution of phenom ABC. Phenom P is precessing. So only one of these include precession. There's a new one called SEOBNR version 3, which includes precession. It's very, very slow to compute. Yeah. Yes, but not with any optimism because of two things. First of all, the circular binary models seem to work extremely well for the events that we've observed. But secondly, this model does not include spin. We do not have a model that includes both eccentricity and spin, and we're pretty sure there's some degeneracies there. And it's only in spiral, no merger or ring down. In other words, good PhD project. As I mentioned, if we had the right model, we'd only need one, but they don't agree with each other. So different waveform families can help us estimate the systematic error associated with our imperfect knowledge of the correct GR prediction. And this is crucial for testing GR. You don't want to fool yourself by picking a model that doesn't quite agree with GR and saying, oh, I got some deviation from GR. That's wrong. Don't do that. So you have to be very careful. Okay, I want to change the subject and talk about other aspects of the waveforms besides their phase evolution, which is still the most important one. But in particular, I want to lead up to understanding the detector response. Okay, this is very important for observation. So detector response. It's based on it requires us to understand polarization. You've already seen pictures like this. Here's the quadrupole formula. Here's the fact that it's a traveling wave. Here's the tensor for a wave traveling in the z direction. Okay, so it has no time components and it has no z components. It only has x, y components, and Tom derived them all for you. And here's the pattern of strain that they make if the gravitational wave is traveling into the board and we choose our arbitrary orientation that up and down and left and right is plus and 45-degree rotated is cross. Okay? So you've all seen that before. Now imagine that the wave is traveling towards the Earth and traveling towards a detector. So here's our detector, the x-arm, the y-arm, the zenith. This is the surface of the Earth. That's the detector plane. So that's one coordinate system, the detector coordinate system. There's another coordinate system way over there, which is the source, okay, which has the orbital plane and maybe it's precessing and all kinds of things like that. And then there's a third coordinate system, which is the wave coordinate system. Here's the plane of the sky. Here is the direction towards the source. And here is one orientation of the polarization. Let's call it plus. And here is an arbitrary orientation in which this plus has been rotated by some angle psi, an azimuthal angle, which, as you can imagine, is it's multivalued in the sense that if you rotate by 45 degrees, you get cross polarization. If you keep rotating, you go back to plus polarization. So really, psi only goes from 0 to pi over 4. Okay? These pi over 4. If you rotate by pi over 2, 90 degrees, then plus polarization rotates into plus polarization with a minus sign. Rotate by 90 degrees, same darn polarization with a minus sign. This one's stretching, this one's squeezing. Rotate, it's doing the opposite. That's just a minus sign. Is that confusing for a lot of people? Okay, you'll let me. Yeah, psi goes from 0 to pi over 4. Here's some angles. This is the polar angle and the azimuthal angle of the in the detector plane. Okay, I left out the third guy, which is the coordinate system of the source. So we got 3 coordinate systems: source, wave, detector. And we have more than one detector. This is crazy. Put it all into one coordinate system, celestial coordinates. Now the angles aren't so simple, but they're just rotations. You've got to take into account the fact that the Earth is rotating. Once per sidereal day. Everybody knows the difference between a sidereal day and a solar day. Who does not know the difference between a sidereal day and a solar day? Oh, too many people. Okay, so a solar day is when the Earth rotates or is facing the sun, rotates, and is still facing the sun. During that time, we've rotated around the sun. In one day, we've rotated 1/365th of the way around the sun. So now it's not just a full rotation, it's a little bit more to face the sun again. So a solar day is a little bit longer than one full rotation with respect to the fixed stars. How much longer? 1 over 365 times less. So it's 1 day, 1 minus 1 1 minus 1 over 365 times 24 hours, which is 23 hours and 56 minutes? 56 minutes. About 1 degree. Thank you. Okay, that's good enough. Well, degrees are not good enough. We need radians. Uh, okay, so a sidereal day, the time of rotation with respect to the fixed stars, a little bit less than a solar day. If you're a solar astronomer, you may not care. If you're a real astronomer, sorry, if you're an extrasolar astronomer, okay, you don't care about solar days except what they do to your telescopes. You care because they warm up more, the whole bit. Solar days are, and traffic travels with solar days, but not the stars. Sidereal day is all that matters for us guys, unless you're doing solar physics. Okay, so so you have to take that into account when the source, you're rotating with respect to the source. Now, if the signal is short, like small fraction of a minute or something like that, you don't have to worry about the fact that the Earth is rotating so much. But if the signal is always on, like a spinning neutron star in our galaxy is producing a continuous sine wave of gravitational waves. It's always on from that direction. Okay? And as the Earth turns, it's hitting the detector from different direction all the time. You must take that into account. Okay? So, how do you take it into account? You compute the detector response. I probably don't want to go through all these details here, but the strain can be written as a plus polarization time series times a tensor basis vector. The tensor basis vector for plus has a 1 here, a -1 here, and zeros everywhere else. The basis vector for cross has a 1 here, a 1 here, and zeros everywhere else. Okay, so these are tensors. You can form these tensors by taking outer products of vectors. In this case, the vector, here's E sub r in the radiation or wave frame. Here's E superscript r, x, and y. And you can take tensor outer products of these unit vectors in this combination to get plus and cross tensor basis tensors. Okay? And then you can compute the detector response by computing the detector tensor. And the detector tensor, here's the X arm of your detector, here's the Y arm, and the LIGO and Virgo detectors detect the difference between changes in the length along this direction and changes in the length along this direction. They are differential arm, DARM, detectors. Okay? Gravitational wave will also stretch in some directions, stretch both arms. That would be a common arm stretch. Okay? LIGO can't detect CARM arm stretches. Why? The Michelson, out the dark port, out the asymmetric port of the beam splitter. What about out the symmetric port of the beam splitter? You're measuring CARM. However, you're also measuring any fluctuation in the laser frequency 8 or 9 orders of magnitude bigger than the gravitational wave strain in the CARM degree of freedom. That's okay. We're going to measure, assume it's all due to laser frequency fluctuations, feed back on the laser to cancel those laser frequency fluctuations, and thereby build the most precisely stabilized laser frequency ever. Why is it the most precise? Because we have 4-kilometer long vacuum tubes with high finesse cavities in them. Nobody else does. We've built the most stable lasers in the world. We have to. Using the CARM, throwing away our ability to measure, if we had any, to measure the CARM motion in response to gravitational waves. Gravitational waves produce CARM. A lot of people go around saying, oh, there's no common mode arm stretching in gravitational waves. Nonsense. Of course there is. We just can't measure it because they're degenerate with laser frequency fluctuations, which are orders and orders of magnitude bigger. So you might recall that either Stefan or Peter talked about optical cavities. And when you measure a deviation of an optical cavity from resonance, you're measuring a deviation of this quantity from an integer. Whatever it could be, it's a large integer because L is large, okay? If you see a deviation from an integer, you're falling off of resonance. You cannot tell what has changed. In LIGO, our length changes by tiny amounts, of course, due to gravitational waves, but it also changes a lot due to all kinds of other motions. So we're constantly noise displacements, and so we can control it this way. But there's this degeneracy. Now, it just so happens that at low fluctuations in L and F, chances are the low frequency fluctuations are due to the mirror going back and forth at that pendulum frequency of about 1 hertz. So then we feed back at low frequencies to stop it from doing that. At high frequencies, it's on a pendulum. It's just not moving at high frequencies. We assume it's laser frequency fluctuations that are changing. And we feed back at higher frequencies on the laser to stabilize the frequency, to keep this at an integer, to keep the arms at resonance. I'm really digressing here. But the point is that you can't, in principle, tell the difference between them. Stefan, I just, yesterday said, I wish we could. I wish we could figure out a way of telling the difference between frequency fluctuations and length fluctuations. And we do have a way. It's called a Michelson. Out the symmetric port of the beam splitter, we assume that this is changing due to frequency fluctuations. And out the dark port, or differential port, or DARM signal, out the asymmetric port of the beam splitter, we assume that the frequency fluctuations have now been canceled, essentially, because really they all reflect back to the laser, and you're seeing length fluctuations. Build a Michelson. That's how you distinguish between them. Okay, so you now have 2 tensors, the detector tensor and the strain tensor. Here's the strain tensor, here's the detector tensor, and you double dot them into each other. You two contractions of indices to get a scalar. And that scalar is the DARM signal. It's the gravitational wave signal. And it's a combination of H plus and H cross. Now, our job is to calculate what that combination is. It's called the antenna response functions. I sure do hope I remembered. I did. Okay. And what you get is that the strain observed in the detector in the differential arm degree of freedom, which is change in the length between the X arm and the Y arm. Well, the change in length of the X arm minus the change in length of the Y arm, that's what's in the numerator, divided by the average length, you don't have to know this terribly precisely, is given by the plus polarized time series, the cross polarized time series, times these factors, which are called the antenna response factors, or functions. And they are these contractions of the detector tensor with the radiation tensor, the wave tensor, basis vectors. Okay? And here they are, nice simple forms, in the coordinate system of the detector, described by theta, phi, psi. Okay? They are functions of theta, phi, and psi. Okay? And you can see from this 2 psi here that only 0 to 2 pi over 4 matter. And here it is for the plus polarization, and here it is for the cross polarization, and they're different. Cosines turn into sines and vice versa. Okay? Now I should say that these formulas are rarely ever used because it's not the coordinate system we want to work in. We want to work in celestial coordinates, and to be honest with you, I don't like trigonometry. I'm going to do all this, I always do all this, in Cartesian coordinates, x, y, z, the celestial coordinate systems. Okay? Z is the North Pole. X is the first point of Aries, if you know what that is. It's a well-defined point in the sky along the equator, and 90 degrees from that, right-handed coordinate system. And then you do it all in Cartesian. You do this tensor arithmetic in Cartesian coordinates. Okay? Both of them. Both indices. So a tensor has 2 indices, 2 tensors contracted. We contract both indices. That's what that double dot means. Okay? Okay, again, these formulas are rarely used, but it's a well-defined problem. We do this all the time. Okay? The antenna patterns that result are complicated. So here it is for plus and cross. These lines over here are the detector arms. Remember, this is all in the detector frame here. So here are the detector arms, X arm and Y arm. And what this shape means is that if a gravitational wave is traveling from the zenith or the nadir, either way, okay, to the detector, and if it is oriented with a polarization angle psi of 0, such that it's stretching space along the X arm and squeezing space along the Y arm, then you get maximal response. By contrast, if you go along one arm, you're not stretching that arm because there's no stretching along the direction of motion. It's transverse to the direction of motion. But you are stretching the other arm. You get exactly half the response. If you go at 45 degrees, you're stretching and squeezing both arms at the same time. 0 response. Okay? And I'll leave it as an exercise to you to understand the cross-polarization antenna pattern. It looks a lot more complicated, even though the formula looks just as simple. Because of these combinations of cosines and sines rather than cosines and cosines, here it's cosine, cosine, sine, sine, here it's cosine, sine, sine, cosine, you can convince yourself that you can get a more complicated pattern. And in particular, for cross-polarization, any gravitational wave traveling in the plane of the detector in any direction but cross-polarized, 0 response. Okay? So our detectors can see the gravitational waves from almost all directions, but not all directions. Okay? Almost all. You could argue, if you average over all these polarizations and directions, that we're not a 4 pi detector, more like a 2 pi detector. Okay? Things get interesting if you consider the possibility that beyond general relativity, there's more than just the plus and cross polarizations, but you could include X and Y vector polarizations, which stretch space along the combination of X and the direction of motion Z, or Y and the direction of motion Z, so longitudinal stretching and squeezing, or pure longitudinal, only stretching in the direction of motion Z, or breathing, in which you're stretching perpendicular to the direction of motion Z, but uniformly in X and Y. So the patterns are, here is plus polarization, here's cross, just 90-degree rotated with respect to that. Here's the breathing mode. Z is in the plane, X and Y just stretch, both. Okay? You'd never detect this with a DARM, differential degree of freedom. Okay? Unless you're in some weird direction. Here's vector polarization. Here's vector polarization. This is the direction of motion, Z. You're stretching in Z and X, or you're stretching in Z, longitudinal, or Y, or just pure longitudinal. Do these pictures make some sense? And then the response functions for a differential arm detector at 90 degrees are these more complicated functions. Exercise for you. What about for ET, where the angles are 60 degrees? Compute and plot the antenna patterns. Oh, you're just going to have so much fun. It's a well-defined problem. Okay? Again, these guys don't exist in general relativity. So if we find them, okay, that's another Nobel Prize. Because first you got to prove that Einstein's right, and then you got to prove that Einstein's wrong. It's 2 Nobel Prizes. We already got the one, now we want the other. Nature has to help out. We'll see. Okay. Okay. This is important because any one detector will only be sensitive to one combination of the polarizations. Okay? If you have 2 detectors and they're not oriented the same, so the angles are going to be different, and they can't be oriented the same. You know, the 2 LIGO detectors are almost oriented the same up to a minus sign. One's like this, and one's like this. Okay? But they're not quite the same because the Earth is curved. Okay? But they're as close as we can get. Why? Why did we orient the Hanford and Livingston detectors almost the same? Confirmation. In other words, well, when we envisioned the initial LIGO detectors and their sites, it was before my time, okay, there was no plans to build other detectors. Well, there were for Virgo, but it was very far away in time. So we were going to build something that was going to detect gravitational waves without any help. And the last thing we wanted was our first gravitational wave to come from a direction where it was seen in one detector but not the other. Because we needed that coincidence to confirm the fact that this little signal on all this noisy data was really present. We needed to see it in 2 different detectors. But what that means is that it's really hard to tell. You can't, in fact, distinguish and disentangle plus and cross. Why is that important? Because if the binary is face on, you're seeing both plus and cross, and you're seeing a signal at like 1, okay, times some whatever factor. If it's edge on, you're only seeing plus and half the signal. Half the signal. So unless you know how much plus and cross you've got, you don't know how far away the source is. In order to make the source to know that, to use it as a standard siren, you need to know its polarization content. And to do that, you need at least 2 non-co-oriented detectors. Does that make sense? Okay. By the way, I use the technical term standard siren. Does everybody know what a standard siren is? You all probably know what a standard candle is, right? Right, a standard candle, you know its brightness, you measure its brightness, you know how far away it is. It falls off like 1 over r squared. Okay? The power, the energy, the brightness of the light. We don't measure brightness, we don't measure power with LIGO, we measure the amplitude, which is the square root of the power. Okay? We measure the amplitude coherently, every wave. You can't do that with optical light. Optical light is 300 terahertz or something like that. Okay, there's no way you're going to follow every signal. You're just measuring the power. You can't see the cycles and measure the amplitude. Okay. But we, and radio telescopes, measure the amplitude and phase of the signal. Okay? That falls off like 1 over r. That's a standard siren. That's acoustic because the frequency is low enough that you can resolve and follow the oscillations. You can do that in acoustic frequencies. That's why we call it a standard siren. Does that make sense? Falls off like 1 over r, not 1 over r squared. But it's not a standard siren, it's a standardizable siren. It's only really a standard siren if you know whether you're seeing both polarizations or only one. And you can only do that when you have multiple detectors. Then it's a standardizable siren and you can measure distance. Furthermore, with one detector, You don't know what direction the signal is coming from. It could be coming from here, here, here. It'll give any old, it'll still give a response. Okay? But with two detectors and more, you can find out where the signal is in the sky. I'll talk more about that later. So you need 2 or 3 detectors to resolve the polarizations, locate the source in the sky, figure out how far away it is. This is all pretty important stuff. By the way, am I near the end? It's 6:30. Okay. Question? Uh, yes, yes, exactly. The only way that LIGO can tell how the binary is oriented is by resolving the polarizations. Is that your question? You cannot do it. Cannot do it. You can't tell the distance. You can't find the thing in the sky. You don't know what the polarizations are. Not much more than that. Except you still can get coincidence for confirmation, unless some joker shook both detectors at the same time. And it happened all the time when we had 2 detectors at Hanford. Not very hard to detect with the 2 Hanford detectors. We never did, of course, because every environmental disturbance affected both of them. One of them was 4 kilometers long, and the other was 2 kilometers long. Okay, why? If you get some displacement disturbance, then you will have some displacement disturbance will produce a strain at the 4-kilometer long detector that's half of what it is for a 2-kilometer long detector. We thought we could use that information. We were stupid. It was useful. Useless. Absolutely useless. Never bought us anything. Oh well. I spent a long time trying to understand correlated noise in the 2 Hanford detectors. A lot of my life. For you. I did it for you. Did it for you. Okay, this is kind of important, and now we want to ask the question, if we don't believe in GR, or if we want to test GR. In fact, if we don't want to test GR, what the heck's wrong with you? Of course you want to test GR. Why do you want to test GR? Because you're physicists. It's trust, but verify. Okay? I'll take one more jab at the astronomers. The astronomers are perfectly happy to just trust. GR is right. Why should I ever worry about that? I want to understand those stars. I want to understand those black holes. I'm going to believe GR, end of story. But when you're a physicist, you want to test GR. When you're a physicist, you want to test the fundamental theory. When you're an astronomer, you want to understand the sources, trusting the fundamental theory. Okay? Yeah. Yeah. 5 or 6. And it just so happens for a DARM type detector, we really can't tell the difference between breathing mode and longitudinal mode. That's right. So for example, in any field theoretic approach to general relativity, there's always, in addition to a tensor field, there's always some scalar field. You almost can't get rid of it. And the scalar field will produce longitudinal or breathing modes. So you want to check to see whether they're there. Yeah. Listen, you guys, for all my little jabs that I do at astronomers, I'm glad that there are people in the audience who jab me back. That's as it should be. Yeah, yeah. So, yeah, the point is that there are plenty of people who wear both hats. And the joy of being in this field is that you get to wear, well, that's the way it is in physics, lots of hats. I'm an electrical engineer. I'm a mechanical engineer. I'm a garbage collector. You wear a lot of hats as a physicist. That's one of the things that makes our world so wonderful. Okay, so enjoy it. Okay. How many, so we can have as much as 5 polarizations? Yes, 6. But again, like I said, for right-angled differential arm detectors, you really can't tell the difference between either of those. You should be able to convince yourself of that fact. Okay, if you don't know the direction to the source, that is. So there's really only 5, scalar, 2 vectors, and 2 tensors. How would you disentangle this? How many detectors do you need? How many non-co-oriented detectors do you need? You need 5. We don't got 5, but we will. Hanford, Livingston, Virgo, Kagra, LIGO, India. We also have GEO, but it's less sensitive, and so on. With ET, in principle, you could do all of this. One detector, of course, as Stefan pointed out, it's actually 6 interferometers. Actually, it's, what did he say? Yeah, 6. Sorry? You're asking whether I think they could be true? That would violate. Probed. So, off the top of my head, I would assume so, but don't know for sure. But I would assume so. I mean, what you're asking is whether ET can distinguish between these two. So Sylvia asked me that question, right, yesterday, and I said, blah, 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 and I thought about it, and then blah, 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 and I said, I need to calculate this. But I think the answer is yes. Okay. You can even do it with one detector. Have you ever heard of this detector, TIGA? Have you ever heard of this detector, TIGA? Okay, TIGA, I think it's in Brazil. You're Schenberg, right, okay. So Schenberg is not a sphere, it's an, whatever, icosahedron, very close to being a sphere. And then what they do is they put 5 strain, it's a big hunk of aluminum, really big hunk of aluminum, cryogenic, and a gravitational wave goes by and shakes it. And depending upon its direction and the polarization, it shakes it in different ways. So you put a bunch of different strain gauges on the faces of the icosahedron, and you can, in principle, disentangle all directions and polarizations if you had the sensitivity to detect it all, which would require money. Okay. I just spent 2 lectures without ever yet talking about the pipelines themselves. I'm going to give you one last slide and then end. So we need to sift through months of 2 or multi-detector data, coincident strain data, to look for signals with durations from seconds to minutes or something like that above the detector noise. So we have 2 different template-based searches. One is designed to be low latency. It's called GST-LAL. It's based on GStreamer, which is third-party software that you have already if you have a Linux computer which does audio streaming and signal processing in the time domain using this thing called GStreamer. It's designed to do signal processing in the time domain in a streaming, time-coherent way. Okay. And then we have more frequency domain searches. Well, PyCBC is a frequency domain search. I think MBTA is also correct, frequency domain search. I don't even know. But I'll talk more about multibanding shortly when I talk about GST-LAL, which is also multibanding. PyCBC was originally an offline, designed to be an offline search. That is to say, you collect the data, and then an hour or a day or a week or a month later, you analyze a big chunk of data. And then, but you want to do things quickly, low latency, tens of seconds, because if you find a signal, especially if it's a binary neutron star, you want to tell every telescope in the world to point there. So you need to do this quick, low latency. Literally tens of seconds after a gravitational wave passes through our detector, and passes through all the detector within tens of milliseconds, because that's light travel time across the Earth. And then we run the data through the pipeline, through the pipelines to do coincidence, which means the data has to come from all detectors to one place, which currently is at Caltech, and except for an MBTA, it's run at a computer in Kashina. And then you find, as I'll describe, potential signals, candidate signals, and within minute or two or three, you're ready to tell the rest of the world and approximately where to point. Okay? And I'll talk much more about that later. We also have searches for short duration unmodeled, non-template based searches, bursts, which you'll hear much more about from Marianne tomorrow, especially coherent wave burst. And there's another one called OLIB. And they all make use of two detector coincidence in both time and signal morphology. Okay? It's possible to detect a gravitational wave, not its location or its polarization, but its presence with only one detector. In fact, you can detect a continuous wave, it's always on, with one detector and even locate it in the sky very accurately if you integrate it for a long period of time over many sidereal days. But for a short one, you need, it's nice to have that coincidence, but if the signal is loud enough that it really stands out, you can do it with one detector. We've never done that yet, but we hope to in the future. All of them estimate the background from assuming that the background is detector noise fluctuations, especially non-Gaussian ones, and assuming that the detector noise fluctuations at Hanford and Livingston and Virgo are uncorrelated. And so if you see a detector noise fluctuation at the same time within milliseconds at both detectors, you can estimate how often that accidental coincidence happens by time shifting the data and looking for accidental time-shifted coincidences. And you can do time shifts every second, 2 seconds, 3 seconds. If you do a time shift and find something coincident by 1 second, it cannot be a real gravitational wave. It does not take 1 second for a gravitational wave to hit at one detector and then another. It takes milliseconds. Okay? So a time shift of 1 second, 2 seconds, 3 seconds, you can do it 10 to the 6 times. So you can get, and we do it more than that, 10 to the 7 times. So we have 10 to the 7 trials of accidental coincidence of instrumental noise. And from those, we can estimate how often you'll see something as loud as your candidate event. And from that, you can calculate a false alarm probability. And if that false alarm probability is less than 10 to the minus 6, you can say 5 sigma. Give me my Nobel Prize. And that's what happened. Okay? Of course, it's certainly possible that there is a disturbance that affects both detectors at the same time. And there are several examples of those, such as a lightning strike halfway between them. Heck, a lightning strike anywhere would produce some EM pulse that would hit the two detectors at the speed of light. Okay? And if that EM pulse would produce something that looks like a gravitational wave in our detector, it would be nearly coincident. However, it would also ring up all of our EM pulse detectors, which we distributed all the way around the site, which are far more sensitive to EM pulses than our gravitational wave detector is. So we can rule those out, okay, for example. The next couple of lectures is all going to be how we do this in practice and how we can get rid of those accidental coincidences. Okay? And that's what I'll pick up with next time.